Hello students, how are you doing? I hope we are all enjoying our lockdown at home and we have been doing one thing or the other. Most importantly, we have not been playing with our studies. We've been very focused. So my name is Dixon Dio, one of the chemistry teachers of GNA School, Ayobo, Lagos. Today we'll be looking at Graham's law of diffusion of gases. There are a whole lot about the gas laws, but today we're focusing on Graham's law formula, or which is popularly known as Graham's law of diffusion. Now, Graham's law states that the rate of diffusion or effusion of the gas is inversely proportional to the square root of its molar mass or vapor density. Now, if you look at this law, there are two key words in this law: diffusion and effusion. So, if you first of all start with diffusion, you will agree with me that diffusion is the movement of solids or gases from a region of higher concentration to a region of lower concentration until they are equally distributed through a material medium. Now, what material medium are we talking about? You could use a classroom, for example, and Mr. Dixon stays in a corner of a classroom, sprays a sweet-smelling perfume, and before you know it, somebody standing at the other extreme of the class, the whole classroom is filled up with the aroma of the perfume and is like, wow. So the same thing applies to the same rate of diffusion. Somebody could stand at the corner of the classroom there and release a foul odor, and the odor is filled up. I remember vividly in one of the classes where you had a student release a foul odor, and probably another one that was having a sweet nap just jumped up. That is diffusion. So where the thing is coming from is from that, and if it's from the door, that is the rate of diffusion. That's the higher concentration to when the odor got to the extreme until a material medium that's filled up the whole place. Now, if you look at this now, you look at effusion. Effusion is the rate of diffusion through a very small aperture or very small space. So, no matter the rate of that particular aperture, the gas is able to have its way or to move from that region to the other place. Now, Graham's law of diffusion here, there are 10 laws. He gave us 10 formulas in which we use in calculating Graham's law of diffusion, but because of the sake of the class, we are going to quickly narrow down to some of these laws. Now, if you say the rate of diffusion you have here, R, is inversely proportional to the molar mass, which you have here. That you also have in some textbook as R is inversely proportional to 1 over square root of M. So, or you could say the rate of diffusion of the gas is inversely proportional to the square root. If it's vapor density, then you are going to replace the molar mass here by the density of the gas. So, for any aperture, you'll be having two gases that will be diffusing. It could be an oxygen gas that is diffusing, or it could be a hydrogen gas that is diffusing. So, while they are diffusing, you will take into cognizance their atomic masses. So the atomic mass of the gas is not what you use at that particular point in time. So when you are doing your calculation before we get to that place, I'll be able to explain more. So look at this, or R into bracket M raised to power half is equal to constant. So if you introduce a constant value, like you have R is inversely proportional to 1 over square root of M. So all I need to do is to remove this value, this sign that is here. So if I remove this sign here, I'm going to have R is equal to K over M. So when my constant value gives me the rate of diffusion multiplied by the molar mass of the gas in question, or the rate at which that gas is diffusing. Now look at this. In this equation, R is equal to rate of diffusion and effusion, and M is the molar mass. Now remember what I said here. If you talk about molar mass, you are considering the gas or the gases that are diffusing at that particular point in time. So if it is oxygen gas, it becomes a diatomic gas, O2. So I will not express it as O. So if I express it as O as a gas, then it becomes just ordinary 16. So but if I'm taking the molar mass of the gas, it becomes O2, and that gives me 16 times 2 grams per mole. So that is further expansion of what we have here. Then generally, this law is used to compare the difference in diffusion and effusion. These are the two key words you have here. Effusion rate between gases, often denoted as gas A and gas B. So for example, I could tell you that a particular gas A with a particular volume is diffusing. Then at the end of the day, another gas again of the same volume is also diffusing. So if gas A and gas B are having the same volume, it could be 1 cubic centimeters, it could be 10 cubic centimeters, they are diffusing at the same rate. So my R1 is equal to R2, which is the rate, which is equal to maybe a 10 centimeter. That's what I'm trying to say here. Then it assumes that temperature and pressure are constant and equivalent between the two gases. So at this rate here, you are marrying a whole lot. Let's take our minds back to Charles' law. When we talked about Charles' law, we talked about the parameters involved, volume and temperature, and pressure is kept constant. When we talked about Boyle's law, we talked about pressure and volume, and we kept temperature constant. So what they are trying to say here is that it assumes that temperature and pressure are constant. So if temperature and pressure are constant, now, like in the case of the other two we demonstrated, we said for Charles' law, this remains constant. For Boyle's law, this remains constant. So we are bringing the two together now and are constant and equivalent between the two gases. When Graham's law is used, for such a comparison, the formula is written as, look at it here. Rate of gas A, this is over rate of gas B, which you can have at R gas A over R gas B, is equal to molar mass of B. That is, if you take the raised to power half, this raised to power half here, if you rewrite it, you have 1 over the square root of the molar mass of the gas that is diffusing over molar mass of gas A, which you also have there. Now let's take this example problem. It said one application of Graham's law is to determine how quickly a gas will effuse. Let's quickly look at this place. How quickly a gas will effuse. What do we mean by that? That means the tiniest of all aperture, very tiny aperture like this that is as minute as anything, then you look at that gas diffusing through it. It could be the tip of a pen. You can see how tiny it is. So for that gas to pass through it, that is how quickly. So what time will it take that gas to pass through that aperture for it to move out from the surrounding container or whatever? How quickly a gas will effuse in relation to another, and quantify the difference in their rate. So if you have it, two of them will diffuse through that small, will effuse through that small aperture. So it's possible that this one will go out at maybe 10 cm per second, and another one goes out at 8. So depending on how quickly that gas, if I'm comparing two gases, but if it's a gas, we're comparing just one. Then for example, if you want to compare the effusion rates of hydrogen, that is, you can see, this is a molecule, or you can say dihydrogen. So if this 2 is not written here, then it is not a gas. So if it is just ordinary H, you are telling us that it is the atomic hydrogen. So in chemistry, once you see something like this, it means it's a gas. So you have hydrogen gas and oxygen gas. You can see the oxygen also written. So the question you ask yourself is that, why is it that they didn't write this one as O, and why didn't they write this as H? Going back to your elementary chemistry of symbols of elements, we all know that hydrogen is the first element on the periodic table. It takes after the first letter, which is H. Oxygen is the 8th atomic element of 8, going by this. So why didn't I write this? So immediately we have this now, and this. So my molar mass here becomes 1 times 2, if we are referring back to that one. And this one gives us what? 16 times 2. That gives us 32 grams per mole. Okay, you can use their molar masses, that is hydrogen and oxygen. Look at this. I see that. That is the 32, giving you 16 times 2 to get this 32, and relate them inversely. What do you mean by relating them inversely? It means you now pick the other one. Is this going to be on top? Is this coming down? So I want to believe that we all had fun in explaining Graham's law of diffusion of gases, and also in our next class we'll be looking at the calculation aspect of this laws. Remember what I said again, that when we'll be looking at the calculation, we'll be considering 10 formulas that deals with rates and the rate of diffusion and the molar mass of the gas, formulas that deals with rate volume of the gas, formulas that deals with rate and molar masses of the gases in question. Then also in the 10th formula, we'll also be looking at equation 9 and 10 of Graham's law of diffusion that covers that covers the rate of diffusion of the gas when we'll be bringing empirical formula into it. So when we're bringing empirical formula into it, it means, okay, we are moving away from that place, how to arrange them and get what we need at the end of the day. If we are bringing empirical formula into it, so let me not let the cat out of the bag. So in our next class, we'll be looking at the calculations involving Graham's law of diffusion. Thank you, class, and have a wonderful day.